didn't know when I scheduled the seminar.
So I have competition.
Yeah,
yeah.
Unfortunately.
Well, and that's the way it is.
They didn't advertise it. Steve Miller is speaking there, for example.
Okay.
Oh. All right.
So then I'm glad that the people who are here made it. Yeah.
Yeah. Thank you, everyone, for being here, which is, of course, more important. All right. So I'm very glad to present my collaborator, Axel Kleinschmidt from the Albert Einstein Institute in Potsdam. He will talk about automorphy in string scattering and small representations.
Thank you very much, Dima, and thanks for the invitation to give this talk. When you asked me, you said I should try to make it at least the first half a bit like a colloquium style. So this is what I will try to do, which might mean that it's a bit different from the talks that you normally listen to, in the sense that there will be quite a bit of sort of trying to draw a broad physics picture in the beginning. So I should say that what I will talk about is based on work with the collaborators that you can see on this slide in different combinations. So of course it includes Dima, and then there is, I think I saw Siddhartha in the audience as well, but it's also with Guillaume Bossard, Philipp Fleig, Henrik Gustafsson, Daniel Persson, and Boris Pioline. Okay, so let me talk about the goal for today. So the goal actually is twofold. What I want to explain to you is, first of all, why automorphic representations occur in string scattering amplitudes. And not only that they occur and what types of automorphic representations do occur, but also how you can use Fourier coefficients or Fourier expansions to extract physical information from these automorphic forms that sit in the automorphic representation. And as I already warned you, I will try to be very broad in the beginning. So just to put some meaning to the words, I will try to explain what is a string scattering amplitude, how does the automorphy come into play. So this will probably be about, I don't know, 20 minutes or so of very general things. Then I will talk about trying to explain the second goal. Why do we care about the Fourier expansions and why do small representations arise in this context? And finally, I will come to something which I hope will be of interest to you as well, namely, can you also reverse the flow of information? Namely, can string theory tell you something about new mathematical objects or new automorphic representations that haven't been considered previously? And I should say this is some long-term project that has been going on over more than 20 years now. And besides the people who are already listed on the first slide, here are some of the main collaborators in this, or main contributors to this thing. So you can see also there's Steve Miller here, who I just hear is giving a talk today in China, but he also contributed to this. Very good. So please feel free to interrupt me at any time, please. Now, so very generally speaking, I wanted to say just one slide about what do we mean when we say a scattering amplitude. So what are these actual objects that will be associated with automorphic representations later on? And the scattering amplitude is a way to characterize or assign probabilities to certain scattering processes. For example, in the way that some big accelerators do. Here I've drawn or shown you a picture of the CERN accelerator, the Large Hadron Collider near Geneva, which is a very big circular accelerator where elementary particles are being accelerated and then brought to some kind of collision. And when they collide, it's like hitting them with a big hammer, and there's a lot of stuff coming out, and computing the scattering amplitude is really trying to see, if you know something about the particles that do collide, what are the possibilities for the results and how do you use these results to test the theory? So this is what the scattering amplitude is physically or experimentally. Now I'm a theoretical physicist, so I'm more interested in how do you compute these things and not in so much in how you set up this accelerator and actually do the measurement. Theoretically, what a scattering amplitude means is that you take a given model, which is typically given by some action functional or some differential equations, and you use it to compute the different probabilities or scattering amplitudes. And then ideally you compare them with the experiment and you discard the model if it doesn't match what has been measured. So the way that you do these kinds of calculations, first of all in quantum field theory, which I will discuss briefly before moving on to string theory. The way that this is done is using the most intuitive way with Feynman diagrams, which goes back maybe to the 1950s or so. So in here, you can see this, so these are meant to be particles that are moving together. Then there's some interaction vertex where something happens with a certain weight or probability G. Then a new particle or some merged particle can appear and it can split again into other things. So this is sort of really meant to be like a sketch of a physical process. And what the theory of scattering amplitudes in quantum field theory or the theory of Feynman diagrams tells you is you have to draw for a given set of what are called the external, here there are 4 external states, all possible diagrams allowed by your theory that connect them. So in particular, you can also have, because you're in quantum theory, you can have some things that look like these loops in between. So this would be a particle that for a short time splits into 2 particles, say particle and its antiparticle, which recombine and then travel on in this way together. And you have to draw all possible diagrams. And then there are rules for turning these diagrams into numbers, or more properly speaking, integrals. As you can imagine, the number of these Feynman diagrams grows very rapidly when you start allowing for all possible interactions, and in particular for these kind of loop diagrams, it gets very tricky. But this is the way that in principle, these scattering amplitudes are computed in quantum field theory, and this is what is being tested at accelerators every day. One thing that I should say is here I've given a certain weight, G, to these interactions that take place at a vertex. And what this arrangement here does normally is it arranges this calculation of the scattering amplitude into a series expansion in this quantity G, which is typically called the coupling constant. There can even be multiple different coupling constants if you have different types of interactions, but let's assume for simplicity there's only one. But the series that you get in this coupling constant from these diagrams is typically an asymptotic series, which means that you also need to add additional, what are in physics called non-perturbative terms. So these are terms that are not analytic, but they're smooth and they're used to get a well-defined function as a function of G for the scattering amplitude. So this is something that is not, that is very important, but most of the calculations just deal with computing a few of these things and trying to get as close as possible to experiment. So this is the story. This was the story in quantum field theory, but I wanted to talk about string theory. So let me generalize this picture to string theory. And so in quantum field theory, elementary particles are depicted or imagined as points that travel along time. In string theory, this is replaced by having a one-dimensional extended object called the string, and that moves on through time. So what happens there is that it sweeps out a 2-dimensional surface. Here in the beginning, for the point particle, you have what is called the world line, which is just a 1-dimensional trajectory in space-time. For the string, you get a 2-dimensional surface that is often called sigma. And now you want to repeat the same story of calculating scattering amplitudes in this picture here. So what you have to do is you have to define what is this theory of strings, or in this picture here of surfaces sigma moving through space-time. And the perturbative picture is that you just have to define a theory of maps. So these are called embedding maps X, how this world sheet sigma is embedded into a target space-time. So this would be something like our universe. It's in general, it's a d-dimensional so-called target space-time that you can think of just as, for example, 1,9-dimensional Minkowski space. So this is just a 10-dimensional space equipped with a non-Euclidean metric -1 and then 9 +1s. And sigma you should think of as a 2-dimensional compact Riemann surface. That's the way that it's most easy to think about. So the picture with the Feynman diagrams that I drew a moment ago, in this context here is replaced now by a picture of these different Riemann surfaces. So this would be a Riemann surface which is called at tree level since it doesn't have any hole. Then there will be Riemann surfaces of genus 1, genus 2, and so on. And this expansion, this perturbative expansion in terms of powers of the coupling constant is now turned into an expansion in terms of Riemann surfaces of different genera. And it's conventional to start this series at gs-1 by pulling out an overall factor. So that the power of gs is very closely related to the Euler characteristic of this surface. So this is what this perturbative scattering amplitude calculation in string theory would look like. Now, I emphasized before that typically these perturbative pictures, they're not sufficient to capture the full story. So there also will be objects that are non-perturbative in nature. And this was, in a slightly different way, one of the key insights in the 1990s. And one of the main names that goes with this is Polchinski. And so this is the realization that string theory not only contains these sort of one-dimensional objects here, but it also contains objects that are of higher dimension, and they are typically called branes as a generalization of the membrane concept. And these are higher dimensional objects, and strings have the property, these perturbative strings have the property that they can end on them. So this is just something that you find out when you study the theory, that you somehow need this for completeness. And one way of realizing this is through this asymptotic series that I talked about in the beginning, which turns out to be incomplete unless you add these additional terms. And this resonates very well with the fact that when you look at these extended objects and you compute, for example, their properties like their mass or something, you will find that in terms of a function of the string coupling, this is a function that is non-analytic around gs equal to 0. So this is a perfectly nice function there at the gs equal to 0, but its Taylor series is identically 0. So you will never be able to see it if you just do a series expansion in gs. So this is sort of the poster child non-perturbative behavior that you can have. And I'm bringing this up here because it will come back later when we talk about automorphic forms and their Fourier expansion. So remember, please, in particular, this sort of non-perturbative behavior. Okay, so this is the non-perturbative things you have there to the perturbative scattering amplitude. And now I will give you an example of a perturbative contribution to an amplitude. As I said before, what you have to do is...
Axel, excuse me, what does it mean, perturbative?
So perturbative, thank you, I should have explained that. So perturbative is the physics term for saying it's a series in a parameter. So in terms of, let me go back. So perturbative would mean just a power series in powers of a parameter.
Thank you. And how should we think about scattering amplitudes?
So scattering amplitudes, you should think about as and you prepare some kind of things very far away that are that come together. So here, the way to look at this picture, for example, or let me go to the one that I will actually compute now or give you the answer for. So this picture here, you should think of as, so there are 4 things which are in some sense external to this process. And here I'm looking at a particular process which involves 4 things that are called graviton, but the name doesn't matter. So you have 4, let's say, particles. You can think of 2 coming in and 2 coming out, or you can think of all of the 4 coming together and something happening in the middle. And the scattering amplitude is the quantity that describes for you if you fix these the characteristics of the external particles that you bring together into the collision. The scattering amplitude is basically giving you a measure of the probability for this process to be realized in the theory.
So probability for this process. And it has something to do with the coupling constant?
Exactly. So this coupling constant here, I called it the string coupling constant GS. This describes in some sense the the strength of the interaction. So you should think these are particles that are attracted or repelled by a certain force with a certain strength. And this strength is measured by this coupling constant. And you can easily, I mean, if you think about this sort of classically, let's say in a billiard table kind of picture, if you have 4 billiard kugels and you shoot, not all possible configurations actually lead to a collision, depending on how you aim the initial billiard balls. And this is also here. So sort of the way that you aim these billiard balls is characterized by these external quantities, namely the momenta and the polarizations. So the momentum basically tells you that, in which direction this particle is moving, and the polarization is some kind of intrinsic additional property, in the same way that, you know, for light, you can have different polarizations. So you have these polarized glasses and things like that. So the light waves can have different internal properties. So these are called polarizations. And the amplitude really is a way of saying, in the given theory, with the given value of the coupling constant, what is the probability that this happens? Does this make sense?
Yeah, thank you very much.
Okay. Yeah, so here indeed, so the coupling constant, this is this string coupling constant that measures the strength of this interaction that I call the string coupling here, GS. And depending on how many holes the Riemann surface has, which I call loops here, L, the weighting is slightly different. So it's really something that is, as you can see, really related to the Euler characteristic of this two-dimensional surface. So you have to, when you want to compute one of these amplitudes in string theory, what you have to do is you have to fix the number of external particles. Here in this case, it's 4. You have to decide on a genus for the Riemann surface, which fixes this power. And then you have to integrate over all possible things that can happen in between. So you have to sum over all these things. And you also have to integrate over all possible shapes of the Riemann surface. So typically there's a moduli space for the Riemann surfaces, and you have to integrate over that, including the position of these external states called punctures in this context. And this produces at the end of the day for you the contribution of this particular genus to the scattering amplitude. So in this case here, when you look at what I've drawn here, so this is a 4 particles. So as I say, these are very specific types of particles called gravitons, related to gravitational waves and things like that. So you can compute their scattering amplitude using the rules of string theory. And when you do that, you find an answer that I've written here. So at first sight, it looks a bit unwieldy. So let me try to explain the different ingredients. Now, so this is only the tree-level contribution, which means that this is the contribution from Riemann surfaces of genus L equal to 0. Sorry, genus 2, which actually I should have, there's probably an offset here that I should have. So the when I say L loops, the genus is L minus 1 times 2, something like this. I apologize, there's an offset between the number of loops and the genus, which is captured in this formula here. So, but tree means it's this, this kind of Riemann surface without any non-trivial cycles. And these 4 things that are called momenta, K1, K2, K3, K4, they are typically repackaged into these so-called Mandelstam variables. So these, whereas the momenta, they are vectors in vector space because they describe the direction of the wave. These quantities here, they are scalar quantities. They are the invariant norms, combinations of these vectors. And it's sufficient to have these 3 quantities here, the Mandelstam variables, to describe all possible configurations. Then this formula contains also this typical weighting by the string coupling. So this is following this thing here for L equal to 0. And then there's a function that involves these Mandelstam variables S, T, and U together with this parameter alpha primed. And this is now something that is very important. So in physics, we typically have to be careful with dimensions. And so there's something that sets the scale. When I draw a diagram of a string like this, somehow there's a characteristic scale that I have to keep in mind, and this is called the string scale, LS, and the square of that is this parameter alpha prime, which appears in many, many formulas that I will show you. So this is, you could think of this as just setting the unit of length, but you can also think of this, and this will become important in a second, as something as setting the scale of energy, because these variables here, these Mandelstam variables, they are related to the energy that you inject into a scattering process. Excuse me. Which means that when one of these combinations, alpha primed as it's called times S, if one of these combinations is small, that means that some energy is very low, very little. And this is something that will become important. And here at the very end of the formula, I've just written schematically something that takes care of these polarization tensors, epsilon 1, epsilon 2, epsilon 3, epsilon 4. So the main point that I want to make here is that there is a very explicit formula that you can compute using the rules of string theory for the scattering amplitude. And it takes this simple form where gamma, of course, is just the usual gamma function. And this was something that was computed in the early days of string theory, so almost 40 years ago. And what is actually amazing about it is that you can compute this formula here as a closed formula. So it's an exact function of this parameter alpha prime and S and T and U. So you know it for all possible combinations. If you just think, okay, this is a calculation that can be done, why not go on to the next Riemann surface, the torus, and do the same calculation there? And if you try to do that, you will not be able, or nobody has been able so far, to find a closed formula that generalizes this one here. So this is something that is quite disappointing in some sense, and it forces you to not compute the full function of alpha prime, but really try to compute it in what is known as the low energy approximation. So as I was saying, this alpha primed in some sense sets the energy scale. So when these quantities here are small, then this is what is called the low energy regime, and you can only compute the amplitude for higher genus diagrams using a series expansion in alpha primed. So, yes, please.
Yeah, when you say compute, does it mean that you can write integral, finite dimensional integral, which represent function, but cannot compute this integral in explicit terms?
So there are, I will be a bit more precise of in what cases you can compute these integrals explicitly. There are some cases where you can, and some cases where you can only determine the structure of the integral. By which I mean you can determine the integrand, which is non-trivial in itself, but it's not always possible to carry out the final integrals. But I will be slightly more precise about this in a second. But there are some cases, especially for one loop and for a two loop, where you can do the integral and get numbers out of it. You can't get a function, but you can get numbers. So so this connects to what is written here, the question that was just asked. So you can, there's a systematic way which has been very popular over the last few years to actually determine the things that need to be integrated. So these are called, they go under the name modular graph forms. So this is a specific way of determining the integrand, because for higher genus surfaces, as I said, you have to integrate over the moduli space of this higher genus surface. For the torus, it's just the upper half plane divided by SL2Z. But I mean, as you go up in genus, the spaces become more complicated. So often it's possible to determine the thing that needs to be integrated, but it's not always possible to carry out this last integral. In the case of the torus, where you integrate over the upper half plane, there are some places where you can actually do the integrals as well. Shall I go on? Okay. Okay, so in this case here, I mean, this low energy approximation is straightforward because all you have to do is you have to expand the gamma functions. So this is what I've written for you here in the next line. If you expand out the gamma functions, these are the first few terms that you find, and in particular, you find the Riemann zeta function evaluated at specific places. And I mean, there's no obstacle to continuing this, but for the moment, I will just focus on these first two terms, because I want to explain a bit what this expansion means in physical terms. So this expansion, when you send this alpha prime, which I said was the string length, if you make this very small, this means that this diameter of this, let's say, tube of this, or this part that goes to the external state of the Riemann surface, and also the intermediate parts actually shrink to lines. So they shrink to zero size. So this, in this limit, you approximate this diagram here by really this diagram that only involves lines. So this looks like a standard Feynman diagram now. So this is, and this is what this term in this expansion represents, the lowest order term in this alpha primed. So this is called the alpha primed expansion that I've written out here because it's in powers of alpha primed. The lowest order term is just something that you could also compute using a Feynman diagram of standard quantum field theory. In this case, the quantum field theory that you would use is the general theory of relativity of Einstein. But clearly here you see there are more terms that you get from string theory, and what they correspond to is the additional degrees of freedom that a string has compared to just the usual gravity theory. These are called massive strings, for example, and they contribute in some kind of effective new interaction vertex in a field theory picture. So if you were to draw these, the same kind of Feynman diagram, what you have to allow for now is a new kind of interaction. So these terms here, they represent new interactions that were not present in Einstein's theory before. So these, in this sense, string theory provides for you a generalization of Einstein's theory. And this is something that goes under the name of an effective quantum field theory. So you look at a theory that is valid up to a certain order in alpha primed. And the price you have to pay for that is that you have to allow for new interactions. Okay, so this was quite a bit of different things. So let me try to summarize and put them into a picture. So I explained that there are these scattering amplitudes, and we talked about two different expansions for them. So one expansion was the expansion in terms of what I call the perturbative parameter, namely the string coupling or the loop expansion, which here is drawn in this direction. So you just, on each of these rows you have, or lines, you have Riemann surfaces of different genus. And the other expansion is the one that I talked about in terms of this parameter alpha primed, which is the low energy expansion, which here I've drawn in this way. So the information I gave you on the previous slide, I've put onto this chart at these two places. So there was this parameter 2 zeta 3 and zeta 5. And these you can really think of as integrals, in this case over the moduli space of this Riemann surface, which is fairly simple, over a certain integrand. And the question that David Kashtan asked is, in which other cases can you do these integrals? So there are a few cases here where I could have written numbers as well, so where you can actually do these integrals. In general, it's not known for many of these dots what actually the number is that should be written next to them. But as I said, what is already quite interesting is here to get the different integrands for this integral over the moduli space of tori. So when you fix in this double expansion, when you fix the order in the string coupling constant, what you're doing is you're looking at something which is one of these rows. And as I said, this is the only case where you have a closed formula for the whole row. For the higher genus surfaces, it becomes very hard to even get a few of these points fixed. And there's no closed formula for the whole line as far as I know. I think there's no a priori obstacle, but it's just something that nobody has been able to do. So, I mean, the way that I've set this up with this two-dimensional diagram is that, of course, now you can ask the question, what happens if I don't fix the order in this expansion? What happens if I fix the order in the other expansion? So let's say I fix a certain order in this alpha primed expansion, and I look at all the contributions in this direction. So I look at a certain energy scale, at a certain order alpha primed, all the perturbative, so 0 loops, 1 loop, 2 loops, 3 loop, and so on, all the different perturbative contributions to the scattering amplitude. And I might also want to include the non-perturbative terms, which are these branes that I talked about a few minutes ago. And now, I mean, the whole point of the talk and what I want to convey is that sometimes you can get this, and this is, I think, pretty amazing. You can get this whole information using just symmetries and sort of by an indirect argument. You don't have to do the calculation to get these different points, but you can do an indirect argument that captures this whole function. And the symmetries that you use, I will talk a bit about them, but in particular, they involve discrete symmetries, which then will lead us to automorphic forms and automorphic representations. And I should stress, maybe it's a good place with this diagram, that really this is something that is quite remarkable, because you can use this to predict certain values here, and this has been done way before somebody was able to actually compute one of these dots using the perturbative Riemann surface. And the predictions turned out to be correct. So this approach is actually quite powerful. Good. So now I have to explain to you what these functions depend on and what the symmetries, the discrete symmetries are. And the function, the variables of the function, they are called moduli fields in physics, and the symmetry is called U-duality. But these are just names. So you will see in a moment what groups or what symmetries they are, and then you can mentally put the name that you prefer to them. Okay. So one example of a modulus, which is like a parameter of the theory, is this coupling constant. So this is something in principle that you can think about freely tuning, and it will make the scattering amplitude change. So the scattering amplitude changes depending on how strong you make such a coupling constant, or in general a modulus. Other typical moduli are related to the background that the string moves in. So in the beginning, I was saying the string theory is a theory of maps from the world sheet to some target, and this is what I mean with background. This is the target, and it can have additional structure, like a metric. It can have certain form fields living on it, and there can also be some not necessarily geometric information that you put on this background that influences the string dynamics. So all of these different sort of parameters that you can fix in the back, they go under the name modulus. Let me give you an example for this, which is that when you have a background that involves a torus. So this is now not the torus of the world sheet, but this is something that the string can move in. So this is in the target space. That's why it can be of arbitrary dimension. It's not necessarily two-dimensional. And here, this picture shows just the case, let's say, where you have one circle. And now something that becomes important is that the string is an extended object. And in particular, if it's a closed string, it can wind non-trivially around this circle. And there's, I mean, the topological number associated with it, the winding number. And there's another number that you can associate with a string, which is the speed with which it rotates around this circle direction, which is called the momentum. And if the circle has a certain radius, you can just for fun imagine what happens if you take the radius and you invert the radius. And if you do this, and at the same time you invert or exchange the this momentum number and the winding number, you go to a different configuration of a string in a different background space. Because now the background space is geometrically different. It has a different size for the circle. And maybe before the winding was large and the momentum was small, and now the two are also interchanged. Now, what is very important, or surprising even, is that from the point of view of string theory, there's no way of telling these two situations apart. So there's a discrete symmetry here. It's just a order 2 symmetry, sending R to 1 over R. Of course, you would go back and forth. That relates different, seemingly different backgrounds for the string, and says that the string theory does not depend on which one you choose. So this is an example of a discrete symmetry in string theory, and sort of the stepping stone for us to understand automorphy. If you have a higher dimensional torus, you don't only have the radii, but you also have sort of the shape, the shear of the torus, and also some other slightly non-geometric information. And it turns out that in this case, so when you're on a d-1 dimensional torus, you actually end up with a discrete symmetry, which is just the special orthogonal group of split signature d-1, d-1 over the integers. So this is the discrete symmetry that is called T-duality, where T either stands for target or for torus, depending on who you talk to. So this is one example of a discrete symmetry in string theory. We need one more. And the other one is called S-duality. So S stands for strong or strong weak. And it's something that is related to this coupling constant GS. It turns out that in string theory, there's not only this coupling constant, but there's another parameter that is called chi here, that goes under the name of Ramond axion, but the name doesn't matter. So there's another parameter called chi that you can put together with the string coupling constant in this way to form a complex number, which actually turns out to live on the upper half plane and to transform under SL2 in the well-known way. And the non-trivial statement here is that if you take now transformations under SL2 and restrict to integer SL2 matrices, these transformations of omega do not change the string theory scattering amplitude. So whatever you do in string theory should be invariant under this discrete transformation here. And now we've seen two examples of discrete symmetries, namely S-duality and T-duality, and physicists are only mildly inventive. They say, okay, if we put the two together, what we get is called U-duality. ST and the next letter is U for unified. And this is something that was done in the mid-90s by Hull and Townsend. And it actually turns out that if you put S and T together to form U-duality, you get a discrete symmetry group of exceptional type. And depending on the dimension of the torus, so this D is the same as the dimension on the torus that I had before, you get different groups. And here I've put them all into one diagram. And you can see that if you take this D to be 6, 7, or 8, it's truly an exceptional group. If you make it a bit smaller, this diagram starts to look more like one of the classical groups, or even to disconnect when you make D very small. I should say from the outset, so these groups here, these are split real groups for us. So this is always the split real form of this Lie group. This is, you can define this arithmetic subgroup, and there's always a quotient by the maximal compact subgroup that you have to take as well. So this is what is called the quantum moduli space of these strings on this particular background. Now, from this, it's not hard to imagine. So these things are what sort of are the parameters of a string scattering amplitude. And you see they have to obey a certain discrete symmetry. So this is where the automorphy comes from. Oh yes, so one thing that I should say, just putting S and T together in terms of the diagram, this is the T part. This was the special orthogonal group. This is the SL2. And when you put them together, it turns out that they connect in this non-trivial way to form the exceptional series, or Cramer-Julia series as it's called. Very good. So here I've drawn again this diagram that I had before, and we want to look at functions for one of these boxes. And the full amplitude, so this is the sum of all these things. This is the full amplitude. If you expand it out, it has an expansion like this in terms of these alpha prime powers. So that means for some historical reasons, this function here is called E00, and this function will be called E10. But the name is not what is important here. What will be important is what automorphic object it is in a second. So these coefficient functions that are called EPQ in general, so they have the property that they are, as I explained, they have to be invariant under U duality, because the string does not care about which of these discrete transformations you do. The string theory amplitude should be invariant. This is one of the properties. Another property is that the functions should be of moderate growth. So that means that if you go to one of the cusps in this moduli space, then there should be a well-defined expansion near this cusp. And in fact, you actually know what the value at the cusps. So for example, if you go to a cusp where you reproduce this number here, which is called the weak coupling cusp, you know exactly this should be a 2 zeta 3. Or if you take this function and go to the cusp, there should be a zeta 5. So these are two properties of these functions. And the third very important property that I will not be able to explain in much detail is that they also have to satisfy differential equations. So these differential equations are a consequence of supersymmetry, which is also an important symmetry of string theory. And if you go through the gymnastics of this supersymmetry for these coefficient functions, you find that they have to satisfy differential equations in this on moduli space, on this G. So now this sort of was the physical motivation or checklist of things we have to satisfy. But of course, you can translate this now into what is the mathematical object. And the mathematical object is that we are looking for spherical automorphic forms on this exceptional split real Lie group.
Sorry, your parameters are moduli space of curves. Moduli space of curves for genus, okay, starting with at least 3, is not kind of something we see in terms of reductive groups. So how do your modular form interact with your parameters, which are modulus of curves?
Yeah. So let me say again. So these, there were two ways in which I used the term moduli space. So these G here, which live in this exceptional Lie group, this is not the moduli space of a curve. So this is a moduli space that, so the curve is something that is associated with these Riemann surfaces. And indeed, I mean, when you go up, there are these things like Schottky problems and also other things with moduli spaces of Riemann surfaces. So this is a moduli space. This is the first way you can use moduli space in terms of the world sheet. The parameters G here in this group that I also call moduli, they are moduli of the background of the space-time. So there is either moduli space on the world sheet or moduli space associated with space-time. So the ones that I'm focusing on in this talk here will be the ones on this space-time group. And well, one thing that we will see is that you can, so these functions here, one of these boxes is associated with an automorphic form on this space-time moduli space, on the space-time symmetry group. And if you look at, you can use this function to extract the different points here, and they will correspond to very specific parts of integrals over this world sheet moduli space. So if you write down the integrand for this world sheet moduli space, in fact, I mean, this is a very complicated moduli space, as you say. Sometimes you can do the integral at this order and then you find agreement. But it's really the main thing that I want to focus on today is this moduli space, which is in space-time, let's say. Does this answer your question?
Is you have parameters let's say, or the genus. When you pick pi, here the point, you have two parameters. One parameters on the x coordinate, and these are more or less, and the other y coordinate, which kind of genus, or which you can integration.
Mm-hmm.
So when you're talking about interpretation in terms of automorphic forms, the parameter of genus should appear somewhere. So where does it appear?
So yeah, so this I will show you a Fourier expansion in a second. So the parameter of the genus here, so this these genus surfaces, they are weighted by the string coupling constant. And so this is a certain order in this y coordinate, in this gs coordinate. And this is something that gs, this coordinate in this direction, is part of these. But so at this point, really, this is, if I just want to compute this number, this is after doing the integral over the moduli of Riemann surfaces. So this will no longer depend on the moduli of this Riemann surface, but it will be the result of an integration over that moduli space of Riemann surfaces.
This I understood, thank you.
Okay. Okay, good. So I see I'm not doing very well with time, but let me continue. So this is, a lot is known about the first of these vertical boxes that I was showing you and that I called E00, E10 is the next one, and the next one in this nomenclature is E01. And it turns out that the first two, actually, they are just given by a maximal parabolic Eisenstein series. And so my notation here for these maximal parabolic Eisenstein series is that I use the first label here to indicate which parabolic subgroup it is. So it's the P1 parabolic for this group ED in the numbering that I showed on the previous transparency. And 3½ sort of measures the inducing character, which is related to just the fundamental weight due to this first co-root alpha 1 check. And this thing that I call H here is the logarithm map from the group to the Cartan subalgebra. So these are amazingly simple answers for a very complicated physical problem, I have to say. So when this was first found, and this was also already 20 years ago, and many people have contributed to this, people were quite amazed that there is such a simple answer. And why is it so, what is so interesting about this? So physically, of course, also mathematically, this sum here over these cosets, this is like a sum over images. And what the fact that the result is just given by a single sum over images means that you only have to compute a single point for this function, compute all its images, and this gives you the full answer, including all these non-perturbative effects. So this is quite astounding that you only have to have like one point to start from, and then everything else is done for you by automorphy. It didn't need to be that case. And indeed, so this is what I was saying before. So consistency requires, I computed for you or showed you before these two particular values down here, 2 zeta 3 and zeta 5. So that means that if you take these functions and they live on this complicated higher dimensional space, so the symmetric space, ED over its compact subgroup divided by this ED over the integers U duality. If you go to a certain cusp, which is the weak coupling cusp, the function should behave in exactly this way, and the other function in this way. And this is something that you can check using constant term calculation. So this is actually what comes out of these things. And once you have this, automorphy does the rest. Oh, I have to go here. So now finally, we are talking a bit about automorphic forms. And this is, I'm sure, something that all of you know. I'm just putting it here to summarize or to fix. So automorphic forms are functions, I will call them eta, in the way that they come up in physics. Typically, they're on some real group divided by some discrete subgroup, but of course, it's better to think about this adelically. They have the correct transformation properties, so they are invariant under the under the discrete subgroup, and they transform in a certain representation of the compact subgroup. And they have moderate growth conditions, and you also want them to be Z-finite, which I here write as eigenfunctions of the set of invariant differential operators. So this is the standard ingredients for an automorphic form on a higher rank group. And the particular cases that came up in string theory are when you have a spherical function, so this representation of K is trivial, and the moderate growth is fixed in terms of these perturbative results from tree level. And it's also easy to see that they are eigenfunctions of the differential operators. Once you go to the adelic framework, there are also Hecker operators. And I should say, as far as I know, I mean, the Eisenstein series are eigenfunctions of the Hecker operators, but I'm not sure that an interpretation of this fact within string theory has been found. So starting from an automorphic form eta, you can use the right regular action to construct an automorphic representation in the standard way. So you just act on the right on the argument. And if you do this, you produce a certain representation. So this right regular action clearly does not upset this discrete invariance. So you can ask this representation that you generate in this way, how does it sit in the space of automorphic forms of G over with G of Q symmetry. And if it's an irreducible constituent in there, you would call it an automorphic representation. This is very rough, but this sort of provides the link from this Eisenstein series to representation theory, as was taught to us long ago by Langlands. Eisenstein series typically correspond to, or generically correspond to, principal series representations of the group. And the question is now, I showed you very specific Eisenstein series that come up in string theory. So these were very specific maximal parabolic or very specific inducing parameters. Is there anything special? Is there anything special about these cases that come out of string theory? Okay. So in order to answer that question, I make a little digression and talk about the Fourier expansion of an automorphic form. In the simplest case, this is just SL2. This is the parameter that we had before on the upper half plane. If you expand out the function that occurs in string theory, which is this one, you get the well-known formula for the Fourier expansion of SL2 non-holomorphic Eisenstein series. So this is a perfectly well-known formula. And here I've even suppressed a number of terms, and I've only written the leading term when you go to the cusp for the Fourier modes. The reason that I'm doing this is that here you see this e to the minus 1 over the string coupling constant. So this is exactly what I asked you to remember in the very beginning, is really indicative of something that is called non-perturbative behavior in physics. So this is something that is smooth but not analytic. And here we see these non-perturbative things hidden in the non-zero Fourier mode. So these are the non-zero Fourier modes in this Fourier expansion. The zero Fourier modes are constant terms. They are just power behaved as you go to the cusp. So the cusp is going here, this parameter to 0, or the usual parameter to I infinity. And there are two power behaved terms, and they turn out to be related to, when you look at the behavior in terms of the string coupling, I hope this relates to the question or partially answers the questions of where the moduli of the Riemann surface or the characteristics of the Riemann surface. This is how you get the different dots on this vertical line in the diagram that I showed. So the lowest dot is the 2 zeta 3. The next dot up, which would be a one loop world sheet, which differs by 2 units in this parameter, gets a different number. And this number is also a number that you can calculate directly using integrals over the world sheet moduli space. So this is, so this has been known for some time. And what is really interesting is that this gives you these non-perturbative terms that are normally very hard to control in physics. Yeah, so this is just saying again what I just said. So constant terms are what are called perturbative. So these are typically power behaved if you choose the right variables. And the Fourier coefficients are the things that have these non-perturbative things which are not, which cannot be expanded in the parameter. There is a terminology I want to introduce together with a certain connection. So this non-zero Fourier mode M here, so this is the Fourier mode, I will often call this parameter the charge of the instanton, because physically this is what it is. So for m equal to 1, this would be a single instanton or instanton of charge 1, and for higher m it would be a higher charge. So this is just the terminology. What is probably more important, but I guess also known to many people in the audience, is that you can associate the Fourier modes to nilpotent elements in the Lie algebra, or more properly in the dual of the Lie algebra. So this is a story that is completely standard, and there's it just served to illustrate a few points, but actually what I want to talk about in terms of automorphic representations, this is where it gets very interesting for these higher rank groups. And let me say a few general words about Fourier expansions on higher rank groups. So when you can pick any unipotent subgroup, and there are many choices for higher rank groups, and define a Fourier coefficient or unipotent period with respect to this unipotent subgroup by just integrating over one period once you fix a unitary character on that subgroup, which is, of course, has to be invariant also under the discrete transformations. So with this definition, you can define for each u and character psi u, you can define for a given eta, for a given automorphic form eta, this Fourier coefficient. And again, this choice of unitary character is in correspondence with a nilpotent element. And in string theory, typically we have very specific choices for these unipotents in mind, namely, let me try to draw this as good as I can. So this is again this diagram of this exceptional group ED. So the first one is this, when you take a maximal parabolic subgroup with a Levy, which is SOD minus 1, D minus 1, which means that you forget about this point, and this is what corresponds to this weak coupling cusp G string going to 0. So the other two choices correspond to, to the other two extremal nodes of the diagram. So this, if you forget about this node, the Levy that you are left with is of type GLD, and this corresponds to what is called the M theory or membrane limit, and the Fourier modes or non-perturbative terms in this case are called M instantons. And another interesting case is when you forget about this last node, which is the cusp where one of the torus radii becomes very large, which is called the decompactification limit, and this relates to black hole effects. So these are three particular choices of unipotent that are quite interesting and important in physics. And the reason that I mentioned this is that because they are so interesting in physics, there has been, or there is knowledge about what you would expect for these Fourier coefficients. So it's, in general, it's not easy to do this kind of integral for a given automorphic form. But if you go to these particular choices of unipotents, there are physics predictions or expectations of what this Fourier coefficient should be, or at least when it should be non-zero. And the reason for this is that, again, there is this supersymmetry which is playing some role, which means that the Fourier coefficients have to vanish for many choices of psi u. And you can phrase this choice of psi u when it has to vanish in terms of nilpotent orbits. The technical term that goes with the supersymmetry property is BPS protection, but it's just a way of saying that there is a certain physical concept that implies vanishing of Fourier coefficients. in particular, for these two cases here, the first two non-trivial cases, what physics tells you is that you can only have non-vanishing Fourier coefficients if this unitary character psi u that you use for computing the Fourier coefficient lies in the closure of the minimal nilpotent orbit, and I will call this Balla-Carta type A1. And for the other function, you have to have that this Fourier, this unitary character or the associated nilpotent element has to be in the closure of the next to minimal nilpotent orbit, which I will call, or which is of Balla-Carta type 2A1. So this means that the automorphic representations that occur in string theory are very special, namely there are small representations. There are the minimal representation and the next to minimal representation of the group. And so from now on, I think I will no longer use this notation E00 and E10, which is not so informative maybe, but I will call this thing here eta min for the minimal representation and this thing eta next to minimal, because these are the spherical vectors in these representations. And yeah, so you could also use the terminology of wavefront set, but I think I'll not spend time on that. So the question is, well, I mean, physics tells you, or this statement about representations tells you, when does a Fourier coefficient vanish? But it's also very important or interesting to know what is the explicit form of the Fourier coefficient. So can you actually calculate this integral? And here the status, I think, is not as good as it could be in terms of, it's easy to say whether it's zero or not, but if it's non-zero, what is the precise functional form? And I think the situation is better if you don't take an arbitrary unipotent, but you take the maximal unipotent. So in this case, these are the coefficients that are called, that I will call Whittaker coefficients. So it's exactly the same definition as before, except for now I'm specializing to the maximal unipotent, and I've also fixed the Borel subgroup. So for these things, there are many more results that are known. For example, it's known that when you take this character, this unitary character on this maximal unipotent to be generic, this integral here, it factorizes over the different places in your adelic ring. When you go to the non-Archimedean places, it's known how to compute this using the Kasselmann-Chalaika formula. And something, for some cases, it's also known, let's say for GLN, at the Archimedean place, there are works by Bump and Stade and people who compute the Archimedean integrals. Something that is more interesting for us, well, maybe that's a personal point of view, is that there is a reduction formula that also allows you to compute this integral here for the Whittaker coefficient when you assume that eta is an Eisenstein series. So this is the case that I was mentioning occurs in string theory. And you can, in those cases, allow this character here to be degenerate, and you can find a general formula for how this integral evaluates in terms of other objects. And let me show this to you. And for this, I fix a bit more notation. So the Eisenstein series is fixed by a choice of weight, lambda, in the dual of the Cartan subalgebra. And using the Weyl vector rho, you can, and the pairing between the dual of the Cartan subalgebra, and this is the same logarithm map, so this is the pairing between H star and H, you can form this Eisenstein series, and this is really the kind of plain vanilla Eisenstein series. There's no non-trivial induction data, it's just a character determined by this weight, the quasi-character. And so now if you fix this character psi n for these groups that I was talking about, what you have to do is you have to give a tuple of d rational numbers. And these are the things that I will call charges, or I called charges before. So this is just saying for each of the simple roots of the group, how the character acts on those spaces. A degenerate character in this case means that some of these mi vanish. And the ones that do not vanish, they select for you a subgroup of this group ED, and I will call this subgroup G primed. And the group that is defined by this has the property that this degenerate character on all of n becomes non-degenerate when you restrict it to the Borel subgroup or the maximal unipotent subgroup in this G primed. So the reduction formula then takes the following form. If I take the Eisenstein series for weight lambda on this group ED, which I here call G, for a degenerate character psi n, and I just give the formula at the identity, it's given by a sum over coset elements. So this is very simple or standard Brouillard gymnastics for getting this coset sum. It's a sum over coset elements with respect to the Weil group of this subgroup. And then what you have is you have these Whittaker coefficients, but now associated with a subgroup. And the character here is the one that is coming from the restriction. So you just compute Whittaker vectors on a smaller group at a slightly different argument in the principal series. And you have to weight them with an intertwiner, which is sort of the standard thing that you know from functional relations. So it's just a product over certain roots using the completed Riemann zeta function. So this is a general reduction formula, and this formula is important here in this context because I was saying that the Eisenstein series that do occur, they have very specific parameters lambda, so they are very particular Eisenstein series, which means that A, many of only very few psi n are allowed, and B, what also happens is that some of these things can vanish, and this is exactly the phenomenon of a small representation, that you don't have the most generic thing, but you only have a subset. So Dima, I just realized that I'm already over time. What is the standard procedure?
Let's say another 10 minutes.
Okay, then I'll try to get to the main points, sorry. Yeah, so here in this case, you can use this formula to show that for this thing that I called eta min, you can have at most a single non-zero m, and for the thing that I called eta next to minimal, you can have at most two non-zero m's, and they have to be associated with disconnected simple roots. So this is type A1 and this is type 2A1. And it actually turns out that you can show that the integral becomes Eulerian. So yeah, so now this is for these Whittaker vectors, but I want to we wanted to compute these Fourier coefficient on some unipotent, which are of physical interest. And now the question is there some kind of formula, let's say generalizing this well-known formula for GLN to the case of ED, where you can express this Fourier coefficient in terms of these Fourier coefficients? And the answer is yes, and this is the work that we did together with Dima and Henrik, Daniel, and Siddhartha, building on earlier results of Dima, Raoul, and Siddhartha. So I'm not giving you the most general theorem here, but I just want to give you a flavor of what the result looks like. So for example, when you take one of these minimal Eisenstein series, and you take this U to be a unipotent radical of a maximal parabolic, and you put this character in the right place, so which means you put it on the root space that defines the maximal parabolic, you actually have an identity between these two things. So you can just, if you want to know this Fourier coefficient, you can just take one of these Whittaker coefficients that are easier to compute, and they have to agree. So this is one example. Another example for this next to minimal representation is, so you have to now take a character which is of rank 2. There's a certain conjugation that you have to do, bringing it to orthogonal simple root spaces, and then you can express this Fourier coefficient on the unipotent, again, in terms of these Whittaker coefficients, together with an adelic integral. So this doesn't destroy Eulerianity of this expression. So there are some technical conditions here. I'm not explaining all of them because this is just to give you a flavor, and there are many more similar results in our paper. Maybe I say just a few words about where these formulas come from. So what we want to have is, or the general structure of these relations is that you have some Fourier coefficient or even the automorphic form, and you write it in terms of a sum or integrals of these Whittaker coefficients. And this is either called linearly determined by, or in the work of Handley and Sayak, a similar concept appears, it's called spanned by. So to get these formulas, what you do is you start with a thing that you want to compute, for example, the Fourier coefficient. And this is defined by a certain element S that defines the unipotent and the character psi. So together they determine this unipotent integration domain. And then you aim at another integration domain, H, which, I mean, another so-called Whittaker pair, which determines another integration domain, where this integration domain in this case should be the one of this Whittaker vector. And you make a continuous deformation from S to H just using a linear function. And it's important that this H minus S commutes with psi. So you just, for t equal to 0, the integration domain is just where you started. For t equal to 1, it will be the one where you want to end up. And as you increase t from 0 to 1, there are certain discrete points where something can happen called critical points, where you have to do things. So what you have to do, what happens in this process is as you increase t, the integration domain grows and grows and grows, because the unipotent in general is smaller than the maximal unipotent. So you want to integrate over more spaces. And when you do this, you might either have to use this root exchange lemma, or you have to do additional Fourier expansions. And also there are certain conjugations that you might have to do. What is important is that, so you can just do this and accumulate all the possible terms that you have here. But for the case of small representations, you can always discard terms that are outside the wavefront set of the form that you're expanding, that you're Fourier expanding. So that means that in general, you will have many, this will be of a complicated type, but if the automorphic representation of eta is small enough, the formula simplifies, and these were the cases I showed you on the previous slide. I'll skip the example because I want to use the last 5 minutes to, as I said, maybe we can reverse also the flow of information to give you some question to think about in case this was familiar to you. So here I've drawn again this diagram that I've shown a number of times, and this is now what I call the minimal representation, the next to minimal representation. And in terms of nilpotent orbits or their Hasse diagram or closure diagram, there are just the lowest two things. I've chosen here E7. But of course, in string theory, there's nothing that prevents you from going to higher and higher order in alpha primed. So this you could call the next to minimal representation. And physically, this is a perfectly valid question. And the question is now, on this diagram here, what kind of wavefront sets do you get? And remember, what identified the wavefront set or the automorphic representation was the Whittaker support of the function, of the automorphic function, or equivalently, the set of differential equations that the function obeyed. And you can also think of this as the annihilator ideal in the universal enveloping algebra. So now, when you think just of this very next one here, which I call next to minimal, you can also, in physics, analyze this Fourier support. And what you find is that actually the Fourier support, or the maximal orbits in the wavefront set, should be supported on two nodes of this diagram. So there's something on this thing called A2 orbit, and there's also something on a 3A1 type of orbit. And my understanding is, but please correct me if I'm wrong, that this is something that is extremely unexpected for usual automorphic representations. So these automorphic representations, normally the maximal orbit is a singleton in the wavefront set. There's a single maximal orbit. Here, the next thing that occurs in string theory has to have two maximal orbits. let me rephrase this in terms of differential equations. The reason for this is the differential equation that this next to minimal function has to satisfy is not that it's an eigenfunction of the Casimir of the invariant differential operator, but actually it satisfies an inhomogeneous equation. So here there's a non-trivial source term, which is the square of the minimal representation. And this square of the minimal representation is responsible for the fact that in general here you get two maximal orbits. So in this particular case for SL2, this equation was solved and this function was determined using different methods in these papers. And also for these higher rank groups, when you generalize this to ED, the corresponding equations are known, and also the solution is known. And maybe I will not go through the details of the solution, which you can look up in these papers, except for saying that the solution is explicitly known. It involves something like a theta series or a double theta series on a certain lattice, and a theta lift of a weird function which is related to invariance on the moduli space of the genus 2 Riemann surface, called Kawasumi-Zhang invariant. I'm happy to answer questions, but I think I should wrap up. So the point is that this function is not Z-finite because of this inhomogeneous equation, and that for me at least means that its place in this automorphic representation theory is not completely clear. There are similar structures that occur in a different context in string theory that I will not touch upon. I just want to point out that the theorems that I was mentioning for relating different coefficients, actually none of our work required Z-finiteness, so we didn't use this in any way. So these theorems should be applicable to this more general situation, but since the actual solution is quite complicated, it's not so straightforward how to do this. Let me end by saying that I think there are many interesting avenues one could explore, and thanks for listening and sorry for going over time.
Thanks.
Questions, please.
So can I ask about the reduction formula, in the many slides before? So so what are the main applications of this? It is I think you mentioned it's used to prove the what's called the so some certain integrals are Eulerian, right? Or
so actually for proving that certain integrals are Eulerian, it's not this is one way of doing it, but it's not the only application of it. So what you can do here, you see this is a non-Eulerian expression in general, because this is a sum of things. If you choose the right small representation, this big sum collapses to a single term, and then you get Eulerian results. So you can use it in this way. Actually, one of the main ways I like to use this formula is if I am given a certain Eisenstein series, and I want to know which automorphic representation does it belong to. So I can just use this formula for different choices of this character psi n to determine when it vanishes or not. So I can detect vanishing of Fourier coefficients by using this formula, because I know when these things vanish. And then using this this kind of result, where is it? This kind of result, since I know this vanishes, I know, the Fourier support has certain properties.
Okay, thanks.
More questions, please?
Yeah, I would like to ask one question.
Sure.
Yeah, so this vanishing Fourier coefficient is only with regard to Eisenstein series. So there's nothing about cusp forms which are more interest in automorphic forms?
Excellent question. So this, let me go back to one of the slides if I can find one with this diagram that I keep showing over and over. Where is one? I have too many slides. Just one second. Let's go here, for example. So the fact that here in these places you have non-zero contributions from the explicit calculation of this tree-level amplitude means that you cannot just have a cusp form. So you know there's something that remains when you go to the cusp. And one question you could ask is, can I make now the story more interesting? So I have something that has some non-cuspidal part and a cuspidal part. So I induce using a cusp form. It's so far these cases have not shown up in physics. It's not excluded that they do, but for this particular problem that I was describing here, it was completely sufficient to use this plain vanilla thing, and you can even use some of the methods that I was describing to rule out that you, on top of these things that don't vanish at the cusp, you have additional things that you could add which vanish at the cusp. So I mean, there's always an ambiguity in solving the differential equation, and you can also rule out these ambiguities. But it's not excluded that in the future you will see things that look like that also in physics. I know that in number theory, typically they are more interesting.
Yeah, exactly. Thank you.
If I may, I can just say something about that, what you said about ruling out the cusp forms. The cusp forms that might come up. Okay, so if you go back to the way Green and Vanhove had set this up, when I got involved, I mean, the appearance of cusp forms would have been deadly because there was absolutely nothing you could do to rule them out from the point of view of physics. They were, unless you had very careful controlled instantons. And what saved the day is that the spectral parameters are in ranges where we know, due to fairly strong results on Ramanujan, I mean, stronger than what Ramanujan and Selberg predict, that there are just no cusp forms in those ranges. But then now that there's control of instantons, that's another way to handle it.
Yeah, so similar equations to this one. For the other things, there's just in the spectrum, at this place in the spectrum of the SL2 invariant operator, there's no cusp form yet.
Ah, okay.
Are there any more questions? Then Axel, maybe you can show one of the slides you skipped near the end.
I didn't skip that many after all, since I went over time. Let me see. So there was one that I skipped over, which was the example, I think, which is probably this one here. I think I skipped over that.
Yeah.
Yeah, so this is explaining this, our result that we have for relating the Fourier coefficient to the Whittaker coefficient in a particular instance, namely the instance of the next to minimal representation in the case of SL4. And for SL4, there's actually a one parameter family of next to minimal representation. So it's not an isolated pointer, there's a full one parameter family, which you can set up using these spherical Eisenstein series, using the middle parabolic. And for any value of S, you get a next to minimal representation. And you can ask the question, now if I take an element from this next to minimal representation, how do I compute these Fourier coefficients, let's say also in the middle parabolic? So this is the unipotent, this is the choice of character, and which is a rank 2 character. And then the formula tells you that this Fourier coefficient that you're interested in is an integral over a certain space, an adelic integral, over translates of this Whittaker coefficient. And this Whittaker coefficient you can compute using this reduction formula that I showed you. And since this, in this particular case, things are nicely balanced, this turns out to be an Eulerian expression. So here, this gamma that you have to do this translation is just a Weil reflection that brings these two non-zero aspects of this character psi u to simple root spaces in this way. So this is psi n is a character on the maximal standard unipotent, and which is what enters in this Whittaker coefficient. So this gamma here is just W2 in this case. And so in this case here, you can use the reduction formula, work out these W's. The integral is just an integral over this one-dimensional space here. And this is the way that the answer looks like. So at the non-Archimedean places, you get something that involves a divisor sum, but also a sum of divisors of this matrix gamma. So in some sense, it's a double divisor or a nested divisor sum, and with something that looks like zeta prefactors. And so this is what you get at the non-Archimedean place. And at the Archimedean place, you can also do the calculation, and you get a product of two Bessel functions. The reason for this is that this is an SL2, which gives you just the standard Bessel function. This is another SL2 that gives you a standard Bessel function. So this is the reduction formula here had a Whittaker function on G primed, and G primed is SL2 times SL2. And the integral just stays there. So, I mean, you can simplify this a bit, but there's no closed special function that describes this integral in general. But you can also do the calculation of this. In this case, you can do this calculation directly. And this was a check for us for this reduction formula that our general result agrees with this direct calculation.
Okay, thank you very much. Are there any more questions? I guess people are getting tired, so thank you again. All right, so we have no talk next week, but in 2 weeks we will have Steve Kudla speaking. See you everyone in 2 weeks.
Okay.
And thanks everyone for coming. And thank you, Axel, of course.
Sure.
For explaining something to us mathematicians.
I hope it was more or less along the lines that you had in mind.
Yes, yes, it was. I slowly understand one term after the other each. So every talk by your group, I understand one new physical term, and maybe so eventually.
Let's hope it's not an asymptotic series.
Very, very nice talk, Axel. Very nice.
Yeah, very good, Axel. Very good.
So if you want, I can send you the slides, then you can give them to people who are interested.
Yes, if you don't mind, I will put a link on the YouTube channel. There is also a description, so I put there a link to the slides.
Okay.
So are you guys at the same beach?
No, I'm on the sea and he's, I think, on the river, right?
Well, it's a lake not far from Potsdam.
A lake.
And Steve is on Black's Beach. That's why he doesn't have the camera on.
He's on the Black Sea.
No, there's Black's Beach in San Diego, which is clothing option.
Ah, I see.
All right. Okay. Well, anyway, I think we can really see how much the subject has grown, and it's very nice presentation. Appreciate, it's hard to believe in such a short period of time, something which, we couldn't talk to each other at all, basically, 10 years ago, and now, I mean, there's tremendous collaboration and results. So this is fantastic.
Yeah, so there's this whole other area that I didn't talk so much about. I only hinted at these modular graph forms that also, of course, Michael was very instrumental in, which seem to have very similar interesting representation theory in terms of these differential equations. So this is something that I'm getting more and more interested in as well.
If I understand correctly, is that sort of calculating a row instead of a column?
So this is, yeah, exactly. So this is related to calculating a row, but not the full row, but it's related to calculating individual dots in this row.
Well, I mean, if you're right. So once you calculate, so we're calculating columns, and the first 2 or 3 columns correspond to small automorphic representations. And then by some Fourier expansions, you can compute dots somehow.
Exactly.
But you can compute rows, and these rows are, I guess that's what you're explaining. And there also you can compute dots, and sometimes you can compute this and that, and they should agree. And